Hello, I'm Professor Blake, and this is GDD 210, Lab 1, Intro to 3D. Until now, you have likely made most of your games in two dimensions. In Unity, this means everything occurs on the X and Y axes. In this lab, we'll introduce the Z axis and start working in 3D. If you haven't done so yet, please download the GDD 210 Lab 1 Unity project from GitHub. The link can be found on the Lab 1 Blackboard module. Once you have downloaded the project, please launch it in Unity 2019.2.1F1. We will start by looking at the scene in the Lab 1.0 Scenes folder. Here you can see we have a simple cube floating in the center of our scene. If you enable Gizmos in your scene view, you can do so by clicking this button here. You can see I've drawn some lines and boxes to orient the scene. The red line represents the x-axis, while the green line the y, and the blue line the z. Working in 3D means that the position value in the transform component of our game objects should be represented by a vector 3. If we select a game object, you'll see the transform has the position field, x, y, and z components. A vector 3 contains three values, x, y, and z, which makes it perfect for holding the values for our positions in 3D space. Currently, our cube's transform shows us that it's resting at position 0, 0, 0. Now let's press the play button and see what we get. As you can see, our cube immediately started moving around in space. Its position in the scene is displayed at the top left of the game, so you can easily track where it is at any time. The cube is moving between -1 and +1 on each axis using a script attached to it. It can be tricky to get a sense for where it is in space, so you can orbit the camera around the cube by moving the mouse. Now let's go ahead and look at the script that's attached to the cube called cube movement and see how it works. Inside our cube movement script, we have a public variable for our on-screen text, and then we have our update function. Remember, inside mono behaviors, update gets called every frame of the game, so this is going to happen continuously. Inside of update, we're simply setting our transform.position to a new vector 3. Remember, vector 3 has an x, y, and z values. So in the x value, I'm using this sine function to oscillate a number between -1 and +1. I do the same in the y value and the z value. So that's going to cause our cube to oscillate at different speeds on each axis, just because I'm multiplying those values by different numbers here. After we move the cube, we update our text to represent the new position so we can tell where it is in the scene. After update, I have an Ontriggerstay function. This is another mono behavior function, and this allows you to draw what are called gizmos into your scene. So you can draw lines, you can draw shapes. I just use it for debugging, or in this case, drawing just things that make it easier to understand what's going on in the scene. Under that, there's another draw gizmos function. This one's called Ontriggerstay and these gizmos will only be drawn when the game object that this script is attached to is selected in the hierarchy. So if we go back to our scene, you can see when I have not selected the cube, how it looks. Let me turn gizmos on here. And then if I select the cube, we get these extra lines that are drawn. So these lines move along each axis individually, so you can see where on that axis the cube is. On-draw gizmos aren't going to be part of this lab necessarily. They're just included to help you visualize and for a reference if you ever want to try to use them in your projects. So another aspect of position to be cognizant of is the difference between local and world space. I'm going to exit play mode here, and inside this cube I'm going to create a sphere. So in the inspector, you can see that the position of this child game object is relative to its parent's position. So if we move our cube to 1 on the y-axis, our sphere's y value is still 0 because it's relative to the cube's. So it's on the same y position as the cube, so it's 0. But its world space y position is actually 1 because that's what its parents is. In your scripts, you can modify a transform's local position by using the local position variable instead of the regular position. So that would look in our script like, instead of transform.position equals new vector 3, there's a local position variable that you could change. So that's going to make this new vector 3 relative to the parent, not in world space. If your game object doesn't have a parent, it'll act the same as world space. So now while our cube is moving all over the scene, you can see our sphere's position has not changed because it's remaining in the same position relative to the cube. So position in 3D space is pretty simple. You just need to remember that you're dealing with that extra z component of the position. And then you have to remember if you're working in world space or local space. Next we will look at rotation in 3D. Okay, so next thing we're going to do is open up the Lab 1.1 scene to get to our rotation example. So rotation in 2D was usually focused around the z-axis of the object. This is the axis that was typically aligned with the camera view as if it were projected out from the camera. So if we looked at this as if it were a 2D game, usually you just had to rotate your object kind of like this for it to make sense in your game. In 3D, objects can rotate on any of their axes. A player in first or third person might rotate their body along the y-axis, like I am in my desk chair. That's the axis running down from their head to their feet. While their up-down aim, where they're looking up and down, rotates along the axis running from their left arm to their right arm. You need to be careful when rotating in 3D, because you need to know what you are rotating relative to. The scene or the world has a constant up, down, left, right, front, back vectors. But a player's left and right changes as the player rotates around the world. So when I rotate this way, my forward vector is this direction, and the world's forward vector might also be that direction, but as soon as I turn this direction, my forward vector is no longer in line with the world's forward vector. So if you hit play in your rotation scene, you can see that when the gizmos are turned on, the dumbbell's X, Y, and Z axis are drawn through it on the example down here. Now as we rotate around our local axes by pressing X, Y, and Z, you can see that the local axis no longer line up with the world axis. So the dumbbell's y-axis points this direction. It's the green axis. But the world y-axis is still up and down, which would be this direction. To rotate around the constant world axis, you can hold Shift and then press X, Y, and Z. First, I'm going to press spacebar to reset our rotation, and then hold Shift. So now I'm on the world y-axis, but if I rotate, so my local y-axis is now pointing this direction. If I hold Shift and press Y, now we're still rotating around the world axis, the world y-axis. So understanding which orientation you're trying to rotate on is important when adding rotation to your 3D games. If we think back to our first person example, we are rotating on the world's y-axis when we want to turn around. Spin like this, for example. But on the player's x-axis when we want to aim up and down. That's the left to right axis that runs through the player. If we look at the weight spin script that's attached to the dumbbell, you can see we have our class here with 3 public variables, one for each direction we want to rotate. These just let us set how fast it's going to spin in that direction. Next we have an update function, which, remember, gets called every frame of your game. So in here we have what handles the rotation of our dumbbell. I'm going to start inside this area here first, because here we're checking to see if the Shift key is pressed, and in here we're saying if it's not pressed. So we started with looking at it not pressed, so that's where I'm going to start going through the rotations. So we're in here where it's checking if we're not pressing Shift, and then it checks if we are holding down the X key, the Y key, or the Z key. So if we're holding the X key, we want to do this rotate function on the transform component. You can see that the rotate function takes 2 parameters. It takes a vector 3 that it calls Eulers, and that's the vector 3 of the rotation you want to perform. And then it takes a space relative to, and that's where you can define if the rotation is on the local rotation or in the world space. So to rotate on the x-axis, we simply pass in a new vector 3. I put the x spin as the value for the x component of the vector 3 because we want to spin at the x spin speed. And multiply that by time.delta time so that it's smooth between different frame rates. So that gives us the vector 3 Euler for the first parameter. For the second parameter, I put in space.self because I want this to rotate on the local axes. So I do the same thing with y and z here. I make sure that in my vector 3 I'm setting y spin to the y component of the vector 3, and on the z key, the z component of the vector 3 set to z spin. So that handles our local rotation. If we go up to where we are holding the Shift key and we should rotate in world space, looks very much the same. If we're pressing the X key, we want to call the rotate function on our transform component. Here I've changed up the vector 3 just to show you that there's a different way you can do it. Here I've used a different rotate function. This rotate function takes in a vector 3 for the axis to rotate on. It takes a float for the angle to rotate, and then it takes our space relative to. So this is the same rotate function as this one, but it allows you to pass in different parameters if you'd like to execute the function a little bit differently. So these work exactly the same. I just wanted to show that there's a couple different ways to use it. So in this rotate function, we've passed in vector3.right because the x-axis is the left to right axis. For the angle that we should rotate, I've passed in our x spin variable times time.delta time. So that's how much it should rotate on this axis. And then for our relative to component, or relative to parameter, I've passed in space.world instead of space.self. You can see those are your only two options. So when you're rotating around the local axes, you want to do self, and for the scene axes, you want to do world. So again, the next two are very similar. If you're pressing the Y key, rotate. The y-axis is the up-down vector, so we pass that in here. The speed we want is our y spin speed times time.delta time, and our space is world space again. And if we're holding down the Z key, we want to rotate on the forward axis. This is that front and back axis. The speed is going to be Z spin speed times time.delta time, and again on the world space, relative to the world space. So that handles rotating in world space and local space. Finally, in the end of the update function, we have, if we're pressing down the space bar, we're going to set our rotation manually. We're not using a function here. We're just setting the values of the rotation. So this one uses this quaternion.slurp function. Because a rotation is a quaternion, to set it manually, we want to use the quaternion class, which provides us with functions to more easily set the value we want. The slurp function takes two quaternions and it interpolates between them by this value t at the as the last parameter. So what that means is we can put in our starting rotation, when the rotation we're at when this update function got called, and then we can put in a rotation that we want to move towards. So quaternion.identity is our default rotation, which is what we started at. So we want to move from where we are currently towards this quaternion.identity, and we want to do it at this rate of time.delta time times 2. This just lets us define how fast we want to move from our current rotation to this rotation. So this function calculates this for us, and it sets our rotation to that value. So we now have several ways that we can set our rotation, and a couple of examples of how you can pass in different parameters, working in different orientations from world space to self space, and then a way of manually setting the rotation using functions inside the quaternion class. Okay, so next we're going to look at the scene in the folder Lab 1.2, moving in 3D. So this scene uses some of the concepts learned in the previous scenes to make a third-person space exploration game. Here we have a spaceship floating around between some planets. We can move through space by pressing the WASD keys and use the spacebar to move up and down. We can also rotate our ship with the mouse. Alright, so if we look at the script on the ship, we have our ship controller class with a couple of public variables for how fast the ship should move and how much it should rotate when we move the mouse using the sensitivity. I also have some particle systems to shoot some lasers out because spaceships need to shoot lasers. Again, we have our update function, and inside of here we start gathering the player's input. So for our movement along the X and the Z axis, X is going to be left to right, Z is going to be forward and backward. We're just setting a float for each one, input X and input Z. For our Y input, we're using spacebar. We default to -1 because if you're not pressing spacebar, we want the ship to go down. If you are pressing spacebar, we just set it to times equals -1, so it becomes positive. Next, we get our input with our rotation. We set a float called turn input equal to this get axis mouse X. So this is going to return a float based on how far the mouse has moved along the x-axis. So when you drag the mouse from left to right, this will give you a high number. If you go right to left, it'll give you a negative number. Next, we perform our rotation using the rotate function on the transform. And I pass in vector3.up because we want to rotate the ship on the y-axis. The amount we want to rotate it is our turn input. We multiply that by our mouse sensitivity, and then we multiply that by delta time. And finally, for the last parameter, which is the relative to space, we want to rotate on our local y-axis, so we put space.self. So now that we've rotated into the direction we want to be facing, we can start moving. So in this example, we want to move forward in the direction the ship's facing, not forward in whatever the forward direction of the scene is. That's why we wanted to get our rotation first and then apply the movement that we want to move. So what we do first is we set our transform.position plus equal, meaning we're going to add to it. So this is all going to be a vector 3 because that's what transform.position is. So we start with transform.forward. So this is the forward vector 3 of our transform. So whatever direction we rotate, if we rotate it a little bit to the left or the right, forward is going to be the forward vector from that rotation. So now we have a vector 3. We can start multiplying that by input z, which is going to be the forward or backward based on if it was the W key or the S key that was pressed. Then we multiply that by move speed so we can make it faster or slower. And then time.delta time. As always in update, we want to use that to smooth out these movements. And that completes the addition to our position. So we've taken our forward vector, multiplied it by something to get the speed right, and applied that to our position. Next, we're going to change the left and right position. So if you're pressing the A or the D key. So here we start with transform.right. So whichever way our ship is rotated, like me in my chair, the vector pointing to the right is going to be going this way. Or I'm actually rotated on camera, so this way. And if I turn here, now my right vector has changed. So again, because we have already rotated, we can now move in the correct direction to our right. Multiply that by the input x, so that's the key A or D, gives us minus or positive. Move speed, how fast we want to move, and then delta time. And for the last one, we do our up-down position. Same thing, we use transform.up. So because we're not really rotating on any other axes, this one's always going to be up anyway, but so transform.up is going to be transform.up no matter which way I rotate on that axis. Input.y, that's what we're getting from the spacebar, either pressing it or not pressing it. Again, we're using move speed and time.delta time, and then at the end I'm just multiplying it by 25% so that we don't move as fast up and down, because it's a little harder to control. Alright, so now we've gathered our input, we've applied our rotation, we've applied our movement, and then we can just shoot some lasers because that's fun to do in a space game. So if we are pressing down mouse button 0, which is the left mouse button, we go through this array of particle systems I've called big lasers, and we just start playing all of the particle systems that are in that array. If we have released the left mouse button, get mouse button up, then we're going to stop playing those particle systems. Small lasers works the same way, it's just changed to right mouse button, so we're using get mouse button 1. So we'll go back into our game and take a look at those and see how this all played out. If I'm clicking the left mouse button, you can see these big lasers. Right mouse button, some little ones. And you can see I'm gathering my input as I move the mouse and then rotate along that y-axis. The ship rotates, and when I press down forward, I move forward in the direction of the ship. If I press right, I move right relative to the direction the ship's facing. Okay, now that we can manipulate the transform components of our 3D game objects, let's look at manipulating them via Unity's physics system. In 2D, we used the Rigidbody 2D and Collider 2D components to connect our game objects to the 2D physics engine. In 3D, we used the Rigidbody and Collider components. Go ahead and navigate to the Lab 1.3 scene 3D physics. So the Rigidbody component tells the physics engine how to simulate physics on this game object and allows you to set a few parameters. I'm going to select the ball game object here because it has a rigid body and a collider, and we're just going to go through each component and see what it all does. So in the rigid body we have a mass field, which is how much mass our body should have, our rigid body. The drag field is how much to decrease the body's velocity over time. So if it's a ball and it's rolling and you want it to just slow down over time, you can give it drag. Whereas angular drag is how much to decrease the rotational speed of our body. So if we were to spin the ball really fast and we wanted to slow down over time, we would set angular drag. Is kinematic can be set to prevent forces from acting upon this rigid body. So if we set it to kinematic and then we threw another ball at this one, it would not receive any of the force of the other ball. The other ball would bounce off of it, but it would not impart any of its force onto the kinematic ball. Interpolation is used to smooth out movements of the body. Don't generally use this. I'm not going to get too much into it right now. And same with collision detection. It just gives you options for controlling when collision events are triggered. Discrete is fine for what we're doing. Inside of constraints, you can lock positions and rotations along certain axes. So if we locked the Y position of the ball and then tried to move it around, it wouldn't be able to bounce up and down at all, but it could still move on the X and the Z axis. So to make our physics-enabled body react with other physics objects, it needs a collider. Here on the ball you can see we have the sphere collider component. Colliders define a shape for the object in the physics simulator. So the model of the object doesn't necessarily dictate how it's going to interact with other physics objects. You have to define a collider mesh instead of just the 3D model. So in the case of our sphere, it should line up perfectly because it's the same size sphere. Each collider has different options to help define its shape, but all of them can be assigned a physics material and can be set to a trigger. So a physics material is an asset you can create in your assets folder. They have bounciness and friction, which can be applied to your physics objects and determine how they interact in the simulation. The isTrigger bool determines if the physics object should collide with other objects or simply register a trigger event but ignore the collision physics. When isTrigger is selected on a collider, scripts attached to the game object on which the rigid-body components involved in the interaction can use the Ontrigger functions, but no physics interaction will occur. If isTrigger is not selected, those scripts can use the onCollision functions, and physics interactions will occur automatically. So that's a little confusing. We'll get more into that when we look at the script, but basically it gives you an option to register that a collision occurred, and you can choose whether that collision causes a physics reaction like a ball bouncing off another ball, or if it will simply register that that event happened, but the physics interaction won't happen. The ball will just go through the other ball. To explain what this means, we can look at the ball bounce game in this scene. Here you can see when I click on this ball, it goes up in the air, and we get a count for how many bounces we've had. If we hit the ground, it goes back to 0, and the ball bounces on the ground. If we go up too high, we hit this red box. It resets our score and says too high. But it doesn't bounce off the red box, it just goes through it. If we open up the ball script, which is attached to our game object, here you can see in the ball class we have a few variables. We have a reference to the rigid body, which is attached to the ball. We have a float for how much power we should apply when we click on the ball, launching it upwards. And then we have a variable for the text so we can update the bounce count. We also have a private integer just to keep track of how many times we've clicked the ball. So the next function you'll see is onMouseDown, and this works because our class inherits from mono behavior and it has a collider on it. So because we have a collider, when we click that collider, any scripts on the game object with the collider can call this onMouseDown function. So again, our ball has a sphere collider attached to it. It also has this ball script. When we click the collider, it'll look for any other scripts like our ball script, and it'll call this onMouseDown function. Inside of this, we use our rigid body reference, and we call this function add force. So add force is going to add a force to our ball in the physics simulation, where on the ground it basically has no velocity in any direction. When we call the add force function, we're going to set a force on it. So that takes a vector 3 for the parameter for the force, and then it takes a force mode as the second parameter. For the first parameter, a force is a direction and a magnitude. So it needs to be the direction we want to push the ball as a vector, but then also the length of that vector determines how powerful that push is. So vector 3.up is just a new vector 3, 0, 1, 0. But we also want to multiply that by our power so that it goes as high as we set this power variable to. So then this becomes a vector pointing up to the power of our variable we set here. The second parameter, force mode, this determines how the force gets applied. So there's a few different options. Some of them use the mass of the object when applying the force. Some of them ignore the mass of the object. It depends what you want to do in your game, which one you choose. For ours, velocity change is fine. It just adds an instant velocity change to the rigid body, ignoring its mass. After we've applied the force to the ball, we increase our count by 1. So count plus plus, we'll just increment it by 1. And then we update our text to show our count. The next function in this script is the onCollisionEnter function. So because our ball has a rigid body on it, when that rigid body detects a collision because of its collider, any other scripts attached to the game object will get this event triggered on them. So when our ball hits the ground, this script gets called onCollisionEnter because we entered a collision with the ground. The parameter gets passed in automatically, collision. That's the collision that occurred. So that's the collision event is the parameter that gets passed in. That has a couple of things like the point at which the collision occurred. It has references to the two rigid bodies that were in the collision, things like that. For our example, we don't really need to use anything from the collision event. All we're going to do is when a collision does occur, because the only thing we can collide with is the ground, we just set our count to 0, and then we update our text. So again, our rigid body is going to call this event whenever it enters a collision on any other scripts attached to the game object. So since our ball script is attached to it, this will get called when we enter a collision. And we're just going to reset our score and update the text. OnCollision has a few different ways you can use it. There's onCollisionEnter, which occurs when a collision happens. There's also onCollisionStay. So this will get called the entire time the collision's occurring. So if the ball hits the ground and stays there, while it's staying on that ground, it's going to keep calling this function. We don't really need that. And then there's also onCollisionExit. So in that case, if the ball hit the ground, stayed there for a second, and then we clicked it again, when it left that collision, it would call this function. That's not what we want either, so we're going to stay with onCollisionEnter. Next, again, we have this Ontriggerstay function. It works just like the collision function. It gets called whenever the rigid body encounters a trigger interaction. So because we have that rigid body, we can get this function called in our script. Now, something to watch for in this one is triggers pass collider parameters, not collision. So this is a reference to the collider with which we interacted. So in the case where our ball is hitting the red box that's floating in the sky, we're going to get a reference to that collider when this trigger gets called. Again, in our example, we don't have to do anything with that, but for future reference, pay attention to collisions having collision parameters and triggers having collider parameters. So because the only thing that our ball is going to have a trigger interaction with is that red box, we don't really need to do any checks in here. We just know that if we hit a trigger, we're going to set our count to 0. And we're going to set our text to say too high. So if we move back into our scene, you can see the on mouse down function executing when we click the ball. When we let it hit the ground, we get a collision event. On collision enter, we reset our score, and the ball has that physics interaction where it bounces and then eventually comes to rest. When we go up in the air too high and we hit the red trigger, you can see our trigger event occurs. There's no physics interaction, we go through it, but we still get to call that function and say we went too high. Next, we'll look at this rocket cube over here. If you hold spacebar, you can see that the cube starts accelerating upwards, and when you release space, it falls back down. This works similarly to the ball, but with an important caveat. This rocket thrust is a constant force, while the ball bouncing is a single impulse. When applying constant forces to a rigid body, we have to do it in the fixed update function, not update. The physics simulation doesn't run every frame like update does, so making changes to the rigid body in those frames would lead to unpredictable behavior. The physics simulation does run every time fixed update is called, so that's the perfect place to apply constant forces. Here inside the rocket script, we have a public variable for our engine being on or off, a reference to the rigid body attached to the game object, a public float for how much thrust we should apply, a public particle system for the flames that come out, and then a public text variable for the text behind the rocket that tells us the upward velocity. So you can see we have a update function and a fixed update function on the rocket. Inside of update, we're not applying any forces because we want to do that in fixed update. But we do want to use update to gather our player input. That's because we want that to be as reactive as possible. So we want to check for input every frame. So inside of update, we check if the spacebar is held down. We set engine on to true. And then we play our flames particle system. If you're not holding down spacebar, we stop the flames particle system. And we set engine on to false. So this way we're checking for spacebar being pressed every frame. It will be as responsive as possible without any kind of input lag. And at the bottom of the update function, we're just setting that string or that text variable to the velocity of the rigid body on the y-axis. So how fast we're going up and down. So now we have the input and we can tell if the rocket should be going up or down. We just need to apply that force to it. And remember, because we're doing this constantly, we want to do it in fixed update. So every time the physics simulation in Unity gets updated, this function will get called. And all we do inside here is we check if engine is on, which we set in update. Then we call the add force function on our rigid body. Here I've passed in the force as a new vector 3, and I've just set our thrust to the y component of the vector 3. So in every fixed update, we're going to add this force, and then I'm using force mode acceleration because it adds a continuous acceleration to the rigid body, which is what we want. And because this is in this if statement, if we stop holding space, next time fixed update gets called, we're not going to apply any force, so it will just naturally fall back down. So by breaking up our input gathering method and our force application method into the two different update functions, update and fixed update, we get the responsiveness of gathering the player input inside of update, which is what we want. We want to check for that every frame. But we apply the forces in fixed update so that we can properly get predictable results from the physics simulation. So as you can see, when we hold spacebar, our velocity increases, our rocket goes up, and when we release spacebar, we fall back down. Because we have box colliders on our rocket and on the ground, that just handles the physics interaction of stopping on it. Our ground doesn't have a rigid body, so it can't move anywhere. The rocket's not gonna impart any force on the ground. The ground's just gonna stop the rocket from moving. So to cover the process of adding a trigger, we're just gonna quickly add one here. So to add this trigger to our scene, I'm going to add a cube above our rocket. I'll just call it trigger. So the box collider that comes with the cube game object just needs to have isTrigger set to true. That way we can call the onTrigger functions in our rocket without blocking it from moving. Next I'm going to go into our rocket script. So under fixed update, I'm going to add the OntriggerEnter function. This is the function that will get called because we entered a collision with a trigger collider. The parameter that it takes is the collider that we interacted with. So this gets passed in automatically. This is going to be that cube that we just added, the collider that's attached to it. So when we enter this trigger, what we want to do is print out the Y position of the cube, just for something to print out. So we can do that with debug.log. We're going to say hit cube, and then to get the Y position of the trigger cube that we hit, we're going to get other, which is the collider that we hit. The collider has a reference to the transform component on that game object, from which we can get the position and then get the Y value. So other is the collider component that we hit. Transform is the transform that's attached to that game object. Position and .y. Now I'm going to add a debug window up here, or a console. Now we can see the message will be printed out. And as we hold space, we will move up through the air. And as soon as we hit the collider, you can see we said hit cube 6.27. If we look at the trigger cube, you can see its Y position is 6.27, so that's correct. And we've just added a trigger interaction. Alright, that covers the concepts we want to look at in Lab 1. We've manipulated positions and rotations of transform components. We've looked at moving in local and world space, the differences between them, and then using the physics simulation in 3D with rigid bodies, colliders, using collisions and trigger functions, and the difference between adding a single impulse and adding force over time inside of the fixed update function. The final scene in here is just some extra physics fun you can play around with and try to figure out how they work. Give you something to try to put in your own games. This ball moving uses a function on the rigid body called add explosive force. We add angular momentum to this cube as we click it, which is the amount of spin on the rigid body. And here we have some joints between these rigid body spheres, so it acts kind of like a chain or something. So these are some topics you can play around with and put together some questions that you want to ask in class, and hopefully get some ideas for some things you want to do for your Lab 1 project.